Guys, this is Jason Stewart. He's going to be talking about physically rendering using Elixir.
So a little while ago, I was facing a dilemma with Elixir. This might be a dilemma that some of you have faced before, or maybe are even facing now. It wasn't whether Elixir is a good language, or is Elixir going to be something I can make money with, or is Elixir going to be around in 10 years? No, it was something else. You see, one of my favorite areas of computer science is computer graphics, specifically photorealistic rendering, where we try to recreate an image using a computer that is indistinguishable from an image you would take in real life. One area where these types of graphics are used heavily nowadays is in movies and television. From the superhero movies that we all love and the special effects we see in those, to the animated classics that enthrall our children, and let's be honest, some adults. And also in movies where the special effects leave a little bit to be desired. These rendering techniques actually try to recreate the physical interactions between lights and surfaces in the scene. The math required is pretty crazy, and the computations that you have to do in these things require so much processing power that sometimes just a single frame in these movies takes hours, if not days, to recreate using huge server clusters. And you see, therein lies my dilemma, because I wanted to create a physically based rendering engine using Elixir. But Elixir is slow. Elixir isn't good for computationally expensive problems. That's what I've always been told. And that really held me back of actually creating one of these things using Elixir. And you might be sitting here in the audience today saying, you know, I have this problem that I really, really want to try an Elixir, but for some reason you have it in your mind that Elixir is not a good fit for that problem. But you know what? You might be wrong. Because there's something about this rendering technique, about this engine, that is very intriguing about doing it in Elixir. And I just couldn't pass up the opportunity to do it. But to understand what that is, we need to dive in. I think it helps to dive in and understand how this rendering engine works. So let's do that. So when we go to render a scene, what makes that scene look realistic when we get it into the final digital image? Well, there's a few things. The first, and maybe the most important, is the shading that we see. When the light hits a material in our scene, does it look realistic? Does wood look like wood? Does metal look like metal? Does skin look like skin? Also, shadows. When one object is blocking another object from light hitting it, does it cast a realistic shadow onto that object? And also, perspective. Do objects that are further away look smaller than objects that are closer to us? We all learned in our high school art classes that we should have perspective correct, so it gives our images a realistic depth of field. But how do we represent that in a digital medium? How do we go about positioning these shapes and rendering such that we have this realism? Well, to understand that, we need to do a little basic math. So when we represent a shape in our scene, it's going to live in a Cartesian coordinate system. This is a three-dimensional coordinate system that consists of an origin point and three axis vectors that are perpendicular to each other. Once we have this defined, we can use points in this system which represent a finite location in that Cartesian coordinate system to position all of our objects, all of our shapes. Now let's do an example to show how this works. Let's imagine that we're going to make a scene out of this theater here. And where I'm standing right now is the origin point of our coordinate system. You can imagine the z-axis running directly towards the back of the auditorium, the y-axis directly upward, and the x-axis directly to my left. From there, we can represent the position of every person in this auditorium using a point. So people that are closer to me are going to have a smaller z value than people further back. People sitting higher up in the back are going to have a higher y value than people lower down closer to me on the floor here. And people to my left will have a positive x value, while people to my right will have a negative x value. Similarly, we can represent direction in our coordinate system using vectors. And vectors are composed of three components that define the magnitude of the vector in each of the axes of the coordinate system. And when we combine a point and a vector, I should note that vectors only deal with direction. If we had the vector 0, 1, 0 pointing directly upward, it doesn't matter if that vector is right here next to me or if it's in the back of the auditorium. It's the same vector. Position has no bearing on vectors. And when we combine a point and a vector, what we get is an array. Array has an origin point where the ray starts from, and it has a direction in which the ray is pointing in. So now we have these basic concepts down for the geometry we're going to use in our scene. Let's talk about how we actually visualize our screen, how we set up the view of what our scene is going to look like when we render it. And we do that with cameras. And the best way to think about a camera in our rendering engine is to picture yourself looking into a room through a window. So you're standing at a point looking through a window, and you can see part of the room through that window. Now you can only see part of it, but if you move closer to that window, you're going to get a wider field of view and be able to see more of what's in that room. If you back away from that window, you're going to see less because your field of view narrows. Now also imagine that we can change the size of that window. We can make it wider or we can make it taller. And when we change the size of it, we can see more or less of it, but we also change the view that we have into that room. If we make it wider and keep the height the same, we might get a widescreen effect, like you see up here in this theater screen here. So we're going to represent it the exact same way in our digital medium. We start with an eye position, which is the position where the camera is going to exist in our scene. In our example, you can imagine that being the point where you were standing looking through the window. Then we define a look at point in our scene. That's the point that we're going to focus on in our scene. And you can envision, again, when you're looking through that window, that's the point in the room that you were focusing on. And then we will define an up direction. This tells us which direction is up for the camera. Now we need to define this because up may not always be up with regards to the scene. Imagine we want to tilt our camera to one side or the other, or maybe even flip it entirely upside down. In that case, the up direction for the camera would actually be down for our scene. But once we have these values defined, we can actually construct a coordinate system for the camera itself. And then we can specify the distance to that window from the camera. We can specify the size of the window, and we can give it a resolution. This is the resolution that the final file will have when we render our image to that file. So a higher resolution is going to give us more detail in our final image. When we have those values defined, we can create our window, and we can subdivide it up and get the actual pixels that we're going to trace and render to our final image. So once we have that, what we can do is we can use that position point on that camera, the position of the camera, and we can use that as an origin point for a set of rays. And we're going to trace a ray through the center of every pixel in our window that we have here. And we're going to trace those out into our scene, and we're going to see if those rays intersect any of the shapes that we have existing in our scene. And if they do, we're going to compute the color value for those rays and return that as the color value for the pixel. Now we get an interesting side effect from this. Because of the way we're tracing these rays out into our scene, we get perspective for free. Objects that are further away from the camera are going to appear smaller than objects that are closer to the camera. And this is pretty neat because remember we said that is one of the things that we need to have for realism in our image. So we get that for free. But before we talk about how we actually compute the color values for each of these rays, let's talk about one other item that lives in our scene, and that's lights. So you might have many different light sources in your scene of varying types and varying sizes. And for this rendering engine, we support two specific types of light sources. And the first one is what we call a positional light source. And a positional light source, examples of that would be the lights you see around the theater here, the glow coming off the screen, these spotlights here, glows coming off of anybody's computer screen that has one open now. It's a light source that is at some finite position in your scene that's giving off a finite amount of illumination. We represent these light sources with a position point, the same we would with any shape that we have living in our scene, and a radius. We specify a radius to indicate the size of the light source. Now, why do we care about the light the size of the light source? Well, this is because we need to take into account something called the solid angle of the light source. The solid angle is the perceived size of the light source from a given point in your scene. So, as an example, imagine I have a light bulb sitting next to my head. The solid angle of that light bulb, when it's this close to my head, is going to be much larger than it would be if that same light bulb were in the back of the theater. And this is important because light sources that are further away give off less light to objects that are further away than it does to objects that are closer to them. So we need to simulate this in our rendering engine. And we can calculate the solid angle for a light if we know the size of it. The other type of light source that we have in our scene are what are called directional light sources. The best example we have of a directional light source is the sun. It's a light source that is so intense, so big, so bright, that we really only care about the direction the light's coming from. We don't care about the size so much. And we represent a directional light source with a direction vector indicating the direction that light's coming from, and the solid angle. We specify that directly. So we specify that directly because we don't really care if we're standing 20 feet that direction, 100 feet that way, 50 feet that direction. When we look at the sun's going to appear the same size from all those locations because it's so big and it's so far away that it doesn't change with those small relative distances. So now that we have those light sources under our belt, let's talk about what happens when we actually trace the ray from our camera through our pixel into the scene. There are three things that can happen with that ray. The first is the ray doesn't intersect anything. It just goes off into infinity and doesn't hit anything. The second is the ray intersects exactly one shape. And the third thing is the ray intersects multiple shapes in the scene. And when this happens, what we have to do is we have to figure out which of those shapes that it intersected is closest to our camera. And that will be the shape that we compute our color values for. All other shapes we can throw away because they're behind that shape and we don't need to know their color values for this pixel. So once we have that intersection point, what do? How do we actually compute the color for that point when we get that intersection point on a shape? Well, there's a few calculations we need to do. But the first thing we're going to do is compute the surface normal for that point. And what the surface normal is it's a vector that's pointing directly outward from the point where the intersection occurred. Now, if you can imagine drawing a tangent line to this point along this sphere right here, the surface normal is going to be perpendicular to that tangent line. And we're going to use this surface normal for a few things. We'll use it in our lighting computations, and we will also use it to trace some additional rays based on the material properties of the shape. So if the shape we have here has it's a material that has a reflective value to it. You might think of a mirror or a very shiny surface that when you look at it, you can actually see reflections of other items in the world reflecting back off of that. What we're going to do is we're actually going to trace another ray out in the scene from this point. And it's going to be the same thing that we did when we traced from the camera to this point. We're going to trace that ray out into our scene, see if it hits anything, any other shapes in the scene. If it does, we'll compute the color value at that point and return that as the reflected ray color for this point. Similarly, if this is a translucent or transparent item, we can send a transmitted ray through the shape and out the back side. And we can send that into our scene, compute any color value, and return that as the transmitted color for this point. Now this allows us to do effects that you might see when you look through a glass or something that has water in it. You get that bent effect or the distorting effect behind it. So we can simulate those type of effects with this transmitted ray. And then finally what we're going to do is we're going to actually do our lighting computations for this point on the surface. But before we do that, what we need to do is we need to figure out what light sources we need to do this computation for. So we're going to send out, for each light source that we have in our scene, we're going to send a shadow ray out towards that light source. And what this allows us to do is we're going to trace this ray, and if it hits any other shape in the scene, we know that that light source we're tracing the shadow ray for is shadowed by some object in the scene for this point. So we're not going to compute the lighting value for it. If all of the light sources turn out to be shadowed, we essentially do no lighting calculation because this point is completely shadowed from all our light sources by objects in the scene. So we're going to take the reflected ray value, the transmitted ray value, and the light color that we compute at this point. We're going to add those together and return that as the color value for this pixel. And we're going to do that for each pixel in our grid. But how do we compute the lighting value? Well, to understand that, you have to understand how our eyes actually perceive color and perceive what materials look like. So when we have a light and we have a point on a surface, that surface material is going to determine how the light reflects off of that. And that reflected light is actually what our eyes see and perceive as color. So that light will come in, and there's two types of reflection that can come off of a surface. The first is a diffuse light, or diffuse reflection. And diffuse light comes off of a surface in all directions equally. And this creates a very matted effect. So you can think of an object that has a lot of diffuse light as like this carpeting, or the shirt I'm wearing, the walls here, or a wall that was painted with a very flat paint. It has a very matted finish to it, not much shine at all. And as you move around those objects and you look at it, you notice the color doesn't change at all. The other type of light that we take into account is specular lighting. And specular lighting reflects off of a surface in a very concentrated manner. These are what you see when you see a shiny object like chrome. It has a highlight to it, has shine to it. And you'll notice that as you move around a really shiny object, the highlight tends to move with it. And the reason that happens is because it's such a concentrated form of reflection that as your angle between the light source is changing, it's actually changing the angle that that light reflection is coming off and your eyes perceiving it. So we need to calculate both of these. And we can actually calculate diffuse lighting very easily. We can be almost exact with our calculation of diffuse lighting. But specular lighting, when it comes to the rendering formula, is something we have to approximate. We cannot compute it exactly. And there are different lighting models that you can use to approximate this type of lighting. And the one we use for this engine is what's called the Cook-Torrance lighting model. And the Cook-Torrance lighting model says that when you get down to the microscopic level of a surface or a material, it's not perfectly smooth. Instead, what you have is you have all these peaks and valleys and crags and pivots that really affect how light comes off of that surface. So instead of having specular light come off at the direction that you would initially think it would come off, what happens is maybe you get a shorter angle because it hits one of those peaks, or you get a longer angle in the reflection because it hit one of those valleys and bounced off in a different direction. And what scientists have done is they've actually gone in with these different materials like brass and paint and gold and jade, and they've shined light onto these surfaces, and with a spectrometer, they've gone and measured at different angles the light intensity coming off of these surfaces. And that's given us a set of normal reflectance data that we can then use to model specular lighting in our rendering engine. So once we have calculated both the diffuse and the specular lighting, we combine those values together and we return that as the light color for that surface at that point. And like I said before, we'll combine that with our transmitted and reflected ray colors, and that will give us the color for our pixel when we trace it. One last thing we need to talk about before we kind of get back to what I stated earlier. We have to do some type of anti-aliasing, because whenever we're rendering to a digital image, we're going to get some level of aliasing in our rendering just because of the nature of digital rendering and the finite size of pixels. So this shows up most notably as like a sawtooth edge along curved surfaces. If there's any gamers in the audience, I'm sure you're very familiar with aliasing, and you know that it can kill the realism of an image very quickly because it doesn't look right. It's not what we see in the real world. So we do anti-aliasing to kind of get rid of these effects. And the anti-aliasing we do for this rendering engine is a form of super sampling. So instead of tracing just a single ray through the center of a pixel, what we're going to do is we're going to subdivide that pixel, and we're going to trace multiple rays through that pixel. And then when we get the color values back for each of those values in the pixel, we're going to average them together using a filter. And we actually use a Bartlett filter, which makes it so that we use the color values that are closer to the center of the ray, are closer to the center of the pixel more than those that are further away. It kind of ends up being like a bell-shaped curve in the average that we apply that towards. And what that does is that ends up smoothing out those edges. You can see the image up here that has no anti-aliasing has very jagged edges to it. As we apply more and more anti-aliasing, it really starts to smooth that out. It blurs the edge. And what that does is when you zoom out, it looks exactly like a smooth edge. You can't tell that there's any blurring at all. So it gives us a much more realistic looking image. So let's get back to my initial point of why I was so intrigued to do this in Elixir. So as crazy as this rendering engine is and this algorithm is, there's something very interesting about it. It's actually embarrassingly parallel, meaning that we can trace every wraith through a pixel completely independently of every other pixel. So we can break the pixel processing and tracing and rendering of those up and do them in parallel. And we all know that Elixir is great at doing parallel processing. And that was just something that I had to try and do in Elixir. So if we look at some of the results, it's kind of hard to see on the screen, but I can post these later. This is a brass sphere that is surrounded by a few positional light sources. And what you see here, it's hard to see, but there's reflections going on in each of these. There's shading, there's shadows being cast. And you can probably see the next image a little better. This is a brass sphere where we're kind of hovering above our surface. We have two directional light sources on either side of the sphere, and there you can see how it's casting shadows down on the surface below it. So if we look at the rendering times for each of these, you can see that with no anti-aliasing, image 1 took about 10 seconds to render, and image 2 took about 11 seconds. And as we add more and more anti-aliasing to this, you can see that the rendering times go up pretty considerably. And that's because we're tracing so many additional rays into our scene to do that anti-aliasing. But you might be asking, are these times good? Are they bad? I mean, so what's the deal? Well, it actually turns out that I had a reference C++ implementation that I could use to compare this with. And it turns out that the Elixir version is about 8 times slower. So what does that mean? Well, it means we're probably not going to be calling Pixar anytime soon saying, hey, I got something for you. But I didn't exactly expect it to be faster. It was actually faster than I thought it would be going into the project. And it wasn't my intent to really make this a production level thing. And I think that's okay because I had a lot of fun doing it. I learned a lot about Elixir doing it. And if you have that idea rolling around in your head that you really want to do an Elixir, that's kind of my encouragement to you. Remember, you don't always have to build something that's production worthy. You can build something to have fun. You can build something to learn. And who knows, you build something, you might actually have the opportunity to inspire some people to do some cool stuff on their own. And I hope that's what I've done today. I hope that you guys have thought this was pretty cool and you find some inspiration from it. Thank you.